Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over the definition of what a group is. Okay, we are looking at the definition of a group in the mathematical arena, um, specifically under the subject of abstract algebra. Okay, so what is a group? Let's take a look at the definition. A group can be defined as a non-empty set G. We're going to call the group G in this example. So we have a non-empty set G with one binary operation, namely multiplication. You can express a group using the notation G comma multiplication enclosed in the parenthesis. G represents the name of the group, and multiplication is the only operation that applies to this set, this non-empty set, which is a group. In order for this to be a group, there are four properties or axioms that must hold true. Okay, let's take a look at them one by one. The first one is closure. So what does closure mean? Closure basically means that after you carry out an operation or a set of operations on the elements of a set, you end up with another element in that set. Okay? So if A and B are in the group G, then the product of A and B have to be in the group G. So it's basically closed under multiplication. Okay, so that's the first condition that must hold true. The second condition is associativity. We all know what the associative property is. In order for a set to be a group, the associative property on multiplication must hold true. So let's say we have three elements, any three elements in the set G, then A times the product of B and C should be the same thing as the product of A and B times C. So whichever way you group the multiplication process, you end up with the same result. Okay, so elements of group G, in order for it to be a group, have to have satisfied the associative property on the operation of multiplication. Now the next is identity. So we all know what the identity element is. An identity element is what you carry out an operation with an element with, and you end up with the element that you started with. Okay? So here it states that there exists element D in G such that D times A is equal to A times D is equal to A. Okay? For all A in G. In this case, D is the identity element because you see when we multiplied D times A, we ended up with the original element, which is A. So D is the identity element. The next condition or axiom that elements of a group must satisfy is inverses. Okay? So for each element in G, there is an inverse, a to the negative 1 of G, such that a times a to the negative 1 is equal to a to the negative 1 times a, and that's equal to D, which is the identity element that we talked about in number 3. All right? This is known as the multiplicative inverse. Okay, so every element in in a group you must have a multiplicative inverse. And how do you check? When you multiply an element with its multiplicative inverse, in any order, you end up with the identity element. Okay, so any set that satisfies these four properties or axioms qualifies as a group. Now, what are some examples of groups? An example of a group are rational numbers. The set of rational numbers, okay, can be denoted by capital letter R. So if you think about all the rational numbers that exist, do they satisfy the associative property? The answer is yes. Whichever order you multiply rational numbers, whichever way you group the product of three or more rational numbers, you end up with the same result. How about closure? Anytime you multiply two rational numbers, you always end up with a rational number. All right? And the identity element of a rational number, think about 1, for example. If you multiply any rational number by 1, what do you get? You end up with that rational number. So in the set of rationals, 1 is the identity element. How about inverses? That's simply the reciprocal, right? The reciprocal of any rational number. Non-zero rational number represents the inverse of that number, because when you multiply any rational by its reciprocal, you end up with the identity element in the set of rationals, which is 1. So we can clearly see that any rational will satisfy all these four conditions in order to form a group. What are some non-examples? Can you think of a set that is not a group? I have one example, and an example that I have are the set of irrationals. Can you see which of these the set of irrationals violate? If you think about the product of two identical irrational numbers, for example, the square root of 5 times the square root of 5, what do you end up with? You end up with 5, which is rational, okay? You're ending up with an element that's not in the set of irrationals. So which of these four conditions does that violate? It violates the closure condition, okay? The product of rationals is not closed. So since the product of rationals is not of irrationals is not closed, then the set of irrational numbers do not form a group. Remember, closure simply means when you take two elements from the same set and carry out an operation, you end up with another element in that set. Okay, and we just showed that irrationals does not satisfy that condition. So that's a non-example of groups. Okay, there are many other sophisticated examples, but I'm just giving you two simple examples and non-examples just to help you understand the basic idea. And one last thing I wanted to highlight is a special type of group known as abelian groups. Okay, that word abelian simply involves the commutative property. Notice we didn't talk about the commutative property in our conditions. All right, so a group does not have to satisfy the commutative property. If a group satisfies the commutative property, then that group has a special name. It's an abelian group. Okay, so a group G is an abelian group if multiplication commutes. So basically the order of multiplication does not matter. That automatically makes your group an abelian group. Thanks so much for taking the time to watch this presentation. We really appreciate it. Feel free to share this content with your friends and subscribe to our channel for updates to other tutorials such as this. If you would like access to the transcripts of these notes, you can visit our website at mathgotserved.com, and you should be able to gain access to it. If you have any questions or comments, feel free to include it in the comment section below this video. Thanks again for watching, and have a wonderful day.